Now that we know how to calculate the electric potential for a point charge, let's do the electric potential for a uniform linear charge density. Let's take our line of charge from negative L to L with some uniform linear charge density lambda and calculate the electric field at a point P, a distance z above the midpoint of this. So we previously have calculated the electric field of this at this point due to this line charge, but now let's calculate the electric potential and see how it's different. Well, actually, a lot of the things are going to be the same. We're first going to identify a small amount of charge, dq, and we'll write that as lambda dx prime being a little bit of length in the x direction. And we'll identify our vectors r prime and r, and then we can calculate curly r, except the benefit here is we don't really need the vector form of curly r, we just need the magnitude, and the magnitude of curly r here is x prime squared plus z squared. Well, we can just put this into our expression for the electric potential at some point. So we know what dq is, and we know what curly r is. And so we get the integral from negative L to L of lambda dx prime over the square root of x prime squared plus z squared. Again, notice that this is a lot simpler. We don't have to worry about any r hats or x hats or y hats or anything. We don't have to have any directions in here. Everything is just a number, just a scalar. Okay, the lambda is a constant, so it can come out of the integral. So we just have an integral from negative L to L of dx prime over the square root of x prime squared plus z squared. Well, this integral can be done, but it's not an easy one to do by hand, so we look this one up. And I'm glad we looked it up because it turns out the result of the integral is the log of the square root of x prime squared plus z squared plus x outside of the square root. And we have to evaluate that between negative L and L. It's a particularly nasty result, but okay, we can just input our boundary conditions here. We input our boundary conditions for negative L and L, and so we get an electric potential as a function of z that looks like this. So again, this is a function of z because we're some distance z above the midpoint of our line of charge, and so this is an electric potential as a function of z. If we wanted to find the electric field as a function of z, we would just take the negative gradient of this. And so we can just easily find that by taking the negative derivative of v with respect to z, and then that will be the electric field that points in the z hat direction. We won't do that here, but one can do that calculation relatively straightforwardly and show that you get the same result that we had for the electric field at a point in the middle of a line of charge with uniform charge density lambda. So this is a really nice way to calculate the electric potential and therefore the electric field at some point, because we can easily calculate the electric potential without any vectors, and then the vectors just come out from taking the gradient.